Welcome back to The Explainer. Today, we're diving straight into a fascinating concept, the speed of life, and how the actual speed of atomic movement acts like this invisible ticking clock that can literally determine life or death. We aren't just crunching textbook numbers here. We're decoding the universe's rhythm to see how mastering the speed of atoms build the modern world we live in today.
So what on earth connects a melting vaccine to a sinking ship? Well, there's actually a mysterious kinetic link between extreme tropical heat and the freezing North Atlantic. On the surface, a life-saving medical drop in rural India and the tragic fate of the RMS Titanic seem, well, worlds apart. But, as we're going to see, they are governed by the exact same mathematical principle, the speed at which molecules react to the temperature of their environment.
Let's talk about chemical kinetics. It turns out chemistry isn't just something that happens in a beaker in a lab somewhere. It's the language of the universe's clock. Kinetics teaches us that the properties of a material aren't fixed at all. A medicine isn't permanently good or bad, and a slab of steel isn't simply strong or weak. Their survival or their ultimate failure is entirely a function of time and temperature. It's this constant, invisible war against entropy.
Okay, here's the famous Arrhenius equation. But don't get bogged down in the algebra. Instead, try viewing this equation like a map. Think of T, or temperature, as the antagonist of our story, and E sub A, the activation energy, as the shield. This equation dictates the rate of decay, represented by the letter K. When the temperature rises, things happen faster. But molecules have a defense mechanism, their activation energy. Overcoming that energy barrier requires heat, and understanding this precise balance is exactly how scientists learned to manipulate time itself. Moving on to our first case study, the vaccine heat crisis, when atoms move too fast. Picture this. Between the 1980s and 2000s, India's universal immunization program faced an absolutely massive challenge. They had to deliver fragile, life-saving vaccines across a scorching geography, all while relying on a pretty unreliable electrical grid. If a delivery truck's cooling system failed during a 40°C summer in Bihar, the Arrhenius effect would kick in and accelerate vaccine spoilage anywhere from 16 to 32 times the normal rate. Literally every 10-degree rise in temperature meant the rate of spoilage doubled or even tripled. Health workers were flying completely blind. Without a constant temperature, those printed expiry dates were basically useless, meaning they were unknowingly injecting millions of kids with ineffective medicine.
So here's what's actually happening at the molecular level. When power outages allow that ambient heat to push molecules over their low activation energy threshold, life-saving medicine is silently destroyed. As thermal energy increases, the atoms inside those delicate vaccine proteins start vibrating violently. And once that thermal energy exceeds the activation energy of the hydrogen bonds holding it all together, bam, the bonds break, the entire protein denatures, meaning it physically unfolds and essentially becomes a dead liquid, totally incapable of triggering an immune response.
And this brilliantly illustrates the sequential rescue mission that chemists launched to interrogate the molecules and save these vaccines. Obviously, they couldn't just change the weather in India, right? So they turned to the data. They mapped out exactly how temperature spikes cause these failures and rolled out a brilliant three-phase master plan to outsmart the environment. Let's break down those steps.
Phase 1 was all about molecular shielding. Scientists added kinetic stabilizers like trehalose or sucrose, which wrapped around the vaccine protein using hydrogen bonds. Think of it like coating a delicate origami crane in hard wax. By doing this, they artificially raised the activation energy required for failure. With a higher shield in place, the fraction of molecules that could vibrate fast enough to break apart just plummeted. They literally rewrote the chemical code of the molecule to make it heat-proof, even at 35°C.
Then came Phase 2, the vaccine vial monitor, or VVM. Because even with a tougher molecule, doctors still needed a way to see the invisible decay. This clever little sticker acts as a chemical spy. It undergoes a solid-state polymerization reaction that is specifically triggered by heat. As the vial absorbs heat over time, a light square slowly turns dark, calculating the total kinetic energy absorbed to perfectly match the vaccine's specific decay rate. It's a visual go-no-go color clock for doctors right there on the bottle.
Finally, Phase 3 tackled the unreliable electricity using phase change materials, or PCMs. By cleverly applying zero-order thermodynamic principles, these specially designed boxes ensured the decay rate stayed at an absolute minimum for up to 4 days without using a single watt of electricity. They used specialized gels with a very specific melting point. When that 45-degree outside heat hit the box, the incoming energy was entirely absorbed as latent heat of fusion to break the solid bonds of the gel. This meant the change in temperature inside the box stayed at exactly 0. Absolute genius.
Okay, let's flip the script and jump into the Titanic steel crisis when atoms freeze.
We're traveling back to 1912 to see the fatal consequences when the Arrhenius equation works against us in extreme cold. The shipbuilders at Harland and Wolff actually tested the ship's steel at 20 degrees Celsius, room temperature, completely missing the kinetic nightmare waiting in the freezing ocean. At room temperature, the steel was highly ductile. Its structural flaws, called dislocations, could easily slide around through the crystal lattice to absorb an impact. But at -2 degrees in the North Atlantic, the thermal energy plummeted. Dislocation movement dropped to near zero. The atoms lacked the activation energy needed to shift, and the steel became kinetically trapped.
This packages the entire kinetic crisis perfectly. Because the temperature dropped so drastically, the velocity of those sliding atoms just plummeted. Kinetics is all about competing rates, right? Well, here, the rate of cracking was pitted against the rate of bending. And since the steel couldn't bend fast enough to absorb the stress of the iceberg, the only kinetic pathway left was to violently shatter.
This brings us to a crucial concept, the ductile to brittle transition, or DBT. This is the specific temperature threshold below which atomic bonds lock in place, causing a material to shatter like glass, instead of yielding. Decades after the sinking, a forensic Charpy impact test swung a pendulum into chilled Titanic-era steel, proving it snapped instantly, while modern steel simply bent. The issue wasn't that the Titanic steel lacked raw strength. The issue was the rate of deformation at low temperatures.
So the atoms literally froze in place. But it gets worse. Early 1900s steelmaking left behind high levels of sulfur and phosphorus impurities, which created these manganese sulfide inclusions inside the hull. In that freezing water, with the steel unable to absorb the impact, these inclusions acted as heterogeneous catalyst. They practically paved a chemical superhighway for cracks to tear through the massive ship at the speed of sound.
To solve this massive vulnerability for future ships, the international community realized they had to change the alloying kinetics, the actual chemical recipe of the steel, to lower its transition temperature. By adding more manganese and stripping out the sulfur, chemists artificially increased the activation energy required for a brittle fracture. Today, we rely on heavy thermal monitoring. Engineers use plots to map this out, ensuring a material's transition point is heavily buffered far, far below the actual real-world temperature it's going to serve in.
Which brings us to mastering the universe clock, the universal takeaway.
Let's synthesize all of this. We've seen what happens when atoms move too fast and when they freeze. And the payoff of mastering these kinetic extremes is huge. Because Indian scientists mastered the kinetics of their cold chain, India was declared polio-free in 2014, and they built a $20 billion vaccine market with drastically reduced wastage. In engineering, World War II Liberty ships were completely re-engineered for cold service temperatures, and in aviation safety today, airplanes use specific materials like aluminum and titanium to completely avoid shattering at -50 degrees cruising altitude. Controlling reaction rates literally changes history.
If there is one single thing you take away from this explainer, let it be this profound realization about the true nature of matter. As the quote says, the chemical behavior of a material isn't a fixed number. It is a rate that changes with the environment. The spontaneity of a fracture or the breakdown of a protein is completely at the mercy of the surrounding temperature.
Speed kills, whether it's the rapid decay of a vaccine in the brutal summer heat or the terrifyingly fast propagation of a crack in a frozen ship. But by understanding the Arrhenius equation, we learn how to slow down time for delicate biological molecules and speed up resilience in massive steel hulls. Control the speed, and we can build the future.
So, look around you. Think about the invisible speed of atoms holding your world together right now, and ask yourself this one final question. How fast will the materials around you react at the temperature of the real world? It's the question that dictates the very shape of our future. Thanks for watching this explainer, keep asking questions, and we'll catch you next time.